reference to the haystack.
However, there are scenarios where you want to do something that Rust doesn't allow by default, and in that scenario you need to use unsafe Rust code. We're going to talk about the various scenarios where you'll need to use unsafe and how you should best deal with this to avoid any issues. Now, just because some code is labeled unsafe doesn't necessarily mean you shouldn't run it. It's just an indication that it's your responsibility to make sure the code works instead of the compiler. So consider the unsafe keyword to just be an extra warning to you to be extra careful working with that section of code. I would say one of the most common uses of unsafe is to interface with C code. So if that's something you need to be doing, I'm actually going to have a dedicated video on working with C in Rust. So we're not going to talk about how to do that in this video, but I'll have a dedicated video for that. So definitely check that out. Now, some of the things you'll be doing if you interface with C, such as working with pointers, that will be talked about in this video, so this video could still be helpful if that's something you're interested in doing. Now we'll get started real quick. I just wanted to say thank you for joining. I'm Caleb, and I wanted to share that I have two good resources for you. One is an intro course to the software development career. This is part of a larger course that I helped instruct, and this is part of the course I encourage you to use Rust out the use of unsafe. But if you want to dereference to access that value, out the use of unsafe. But if you want to dereference to access that value, then you need unsafe. So what would this look like? We'll start with just a basic variable. We'll create a variable called a and give it the value 10. To create a pointer to this, you'll say let whatever you want to call the pointer. The type of this is going to be asterisk const and then whatever type you're pointing to, and then the address of a. So this is a raw pointer. To use this, we will dereference using the asterisk character. So an example of where you might want to do this is if you wanted to print line and print this value, we'll just say the value is, and then we will dereference the pointer. Hovering over this, you'll get an error. This operation is unsafe and requires an unsafe function or block. To fix this, it's very simple. All we have to do is say unsafe, open the curly brace, close the curly brace, and put the print line inside. So when we run, we should get the value 10 in the terminal. The value is 10. Great, so that is the first example. Now you might be working with a pointer directly like this, or you might need to take a smart pointer and convert it to a raw pointer. So we will surround this with box, and now we have a smart pointer. We just need to do one additional step of adding an asterisk in here. So asterisk A will unbox A, giving us the value 10, and then we get a pointer to that, which is assigned to this pointer variable. To dereference this, we have to use unsafe. But generally, you would just use a smart pointer instead of a raw pointer. So if you don't need the raw pointer for some reason, then just stick to using box. The issue with raw pointers is that when you dereference them, they could be null, and an example of how to do this would be pointer null. And this will create a null pointer, and you're going to have to import this. So quick fix, import standard pointer. And now when we run this, we get segmentation fault. That's bad, by the way. So you never want to dereference null pointers. So this unsafe section isn't always unsafe, but it could be unsafe. But just because it's labeled unsafe doesn't mean you should just leave it as is, saying, hey, this might be a null pointer. Instead, you should do the extra work to make sure that this code works correctly. So that checking is then put on you, so you have to make sure the code's correct instead of just relying on the smart pointers and the compiler. So while this example is kind of silly because we know it's a null pointer, in a scenario where you may not know, you can check. So you can say if, and we can check to see if the pointer, and then anybody calling it will need to surround it with unsafe. So to do this, we'll say fn test and now the next scenario where you might need to use unsafe is if you are working with an unsafe function. So you can label an entire function as unsafe, and then anybody calling it will need to surround it with unsafe. So to do this, we'll say fn test, and all this is going to do is pretty much what we've been doing here. So I'm just going to move this inside of the function. So now we have a test function and a main function. Now if we want to label this function as unsafe, we can just do that here. So we'll say unsafe function test, and we can remove the unsafe inside. So now we don't have to worry about any of that unsafe action. We can just put it on the function signature and make the caller deal with it. So we don't have to worry about it in the function, but we do have to worry about it outside of the function. So if we try to invoke test here, we're going to get an error. Same issue, it's unsafe and requires an unsafe function. So we'll just wrap it in unsafe. Now our code's going to work pretty much exactly the same way as it did before. We can say cargo run, and nothing happens because the pointer is null, but let's give it the value of a, and now we should get the value as 10. So unsafe in the function definition just propagates the issue up to the caller. Pretty similar to if you threw an exception inside of a function, but you didn't catch that exception, it's just going to propagate up the call stack. And now we should get the value as 10. So unsafe in the function definition just propagates the issue up to the caller. Pretty similar to if you threw an exception inside of a function, but you didn't catch that exception, it's just going to propagate up the call stack, and whoever called that function then has to deal with the problem. Now it is fairly common to create a safe interface for working with your unsafe code. So instead of labeling your function as unsafe, just as a quick example, we can remove that here and surround this section with unsafe, and doing this we will no longer be required to wrap the call in unsafe, so we can just use test directly. And this is with the big assumption that function creator adequately tested safety. So basically we're creating a promise to the caller saying, hey, we're using unsafe in here, but the function is not unsafe, so you can rest assured that your function is going to work because we have done all the testing we need to make sure it's not going to go south. Let's now go over the next scenario where you need unsafe, and that is if you want to modify static data. So we can create a global static value up here above main by saying static, and we'll just create some numeric data. We'll just call it points, okay? And this is going to be of type I32, and we'll just give this the value 10. Now to use this, we would just use it like any other variable, nothing too special. So we'll just throw this in here in all caps, and we should be able to run and get the value 10 as expected. So first off, you should generally be careful with global variables, and if you're going to be working with mutable global variables in a multi-threaded situation, and you have two threads trying to access and mutate the static data, this could lead to a race condition, and because of that, if you want to make this mutable, you have to use unsafe. So to actually label this mutable, we will use mutable. This section is okay, we don't have to label that as unsafe, but if we want to then use it, we will need to surround it in unsafe. And again, you get that same error. Data races will cause undefined behavior. So if you're confident you're doing things correctly, then you can safely do this and tell the compiler, hey, it's okay, by surrounding this in unsafe. And now you could go in here and say, for example, points plus equals 1, and we get the value 11. Now I want to talk about unsafe traits, and for this I'm actually going to go back to our previous example, so I'm going to undo. So we can create a trait for things to implement, and we can label it unsafe. I'm actually going to go back to our previous example, so I'm going to undo. So we can create a trait for things to implement, and we can label it unsafe. So to do this, we'll say unsafe trait, give it some name, we'll call it test trait. So I'm going to undo. So we can create a trait for things to implement, and we can label it unsafe. So to do this, we'll say unsafe trait, give it some name, we'll call it test trait, and say that to implement this trait, you will need to create one function called test. So we'll say unsafe function test, and that's exactly what we have defined down here. But say we wanted to add this trait to some type, you would say unsafe implementation, and then the name to create one function called test. So we'll say unsafe function test, and that's exactly what we have defined down here. But say we wanted to add this trait to some type, you would say unsafe implementation, and then the name test trait, and then for whatever type, such as I32, and then we will surround this entire thing in curly braces, so it'll look like this, and then we will label this function as unsafe. So if we want to extend a type and we know that the extension is going to need to be unsafe, we will define it as a trait, labeling the trait as unsafe, and then any functions that are unsafe, label those as unsafe. And then when you invoke this, you would say something like, know that in curly braces, so it'll look like this, and then we will label this function as unsafe. So if we want to extend a type and we know that the extension is going to need to be unsafe, we will define it as a trait, labeling the trait as unsafe, and then any functions that are unsafe, label those as unsafe, and then when you invoke this, we will label this function as unsafe. So if we want to extend a type and we know that the extension is going to need to be unsafe, we will define it as a trait, labeling the trait as unsafe, and then any functions that are unsafe, label those as unsafe, and then when you invoke this, you would say something like I32 : test, and this is going to give us that same error, so you would need to surround this in unsafe. Next up, I want to talk about our last example of when you need to use unsafe, and that is when you're working with unions. So for this, I'm just going to clear out what we have and just go back to having a main function. So unions, they're kind of like enums in that they let you choose a single value. Let's talk about how we would define one. We would say you're going to have an associated value, number of points that you get, and then the way you would use this is inside of main, you could say let win be an instance of win, passing in a value to one of these. So let's say we won silver and we got 30 points. So this is the structure for creating a union, and if you hover over win, the lowercase win, our variable, the type is win. So we basically just created a custom type, kind of like an enum where you choose one of these values and then you'll have an associated value with it. Taking a look at the Wikipedia article for unions, and it's a value that may have any of, basically just created a custom type, kind of like an enum where you choose one of these values and then you'll have an associated value with it. Taking a look at the Wikipedia article for unions, and it's a value that may have any of several representations within the same position in memory that consists of a variable. So we basically just built that structure. We created a type with one of many states that holds a variable. So we created that union, but we haven't used unsafe. We don't need to use unsafe until we try to access that field. So if we wanted to say print this, we would say win dot, and then the field that we chose, so silver in this case, and this will give us that same error. So this is where we would need to surround this in unsafe. So we will open and then close, and now we should be good. We can run and we see we get the value 30 as we expected. Now the thing with this union is that it's called an untagged union because it doesn't keep track of the data type and is therefore only used in a type unsafe way. This is in contrast to enumerations, so I'm going to show you a variation which will use an enum to achieve the same result. And in that scenario, it would be a tagged union. So here's the tagged union Wikipedia page, and it mentions enums from Rust. And you can do more reading on the details of this here. I'm just going to show you a quick example of how you could use this in a similar way where we have an associated value with an enum. That's one of the cool things, is that enums can have values associated with the different field options. So we will change this from a union to an enum, and then instead of a colon and then the type, you will use parentheses, and then say that which of those options you want to select. So same value as last time, just use some from access to it. So a little bit more verbose if you're not familiar with this syntax. Most of the unsafe stuff is going to come up when you are interacting with other languages. So if you're working with C and you have pointers or unions or whatever it may be, then that scenario might come up in Rust. But I just wouldn't by default choose a union. I would always go for an enum. You will need to use unsafe when interfacing with C, so if you want to see how to do that, then check out the video that I'll be releasing on that. That's going to take a lot of this unsafe stuff and show some practical examples where you're going to need to use this.
I don't know about you, but sometimes I get tired of playing it safe. Sometimes I want to live life dangerously. And if you feel the same way, then today's video is especially for you. In today's video, I'm kicking off the Advanced Rust series by talking about writing unsafe Rust code. So take off your helmets, unbuckle your seatbelts, and let's get freaking rusty. So far, all the code we have written has been enforced to follow Rust memory safety guarantees at compile time. However, if we want to opt out of these memory safety guarantees, then we can use unsafe Rust. Unsafe Rust exists for two reasons. Reason number one is that static analysis is conservative by nature. So Rust will So far, all the code we have written has been enforced to follow Rust memory safety guarantees at compile time. However, if we want to opt out of these memory safety guarantees, then we can use unsafe Rust. Unsafe Rust exists for two reasons. Reason number one is that static analysis is conservative by nature. So Rust will reject a valid program if it can't guarantee that that program is memory safe, even though you as the developer know that the program is memory safe. The second reason is that the underlying computer hardware is inherently unsafe. If Rust didn't allow you to do unsafe operations, then you couldn't do certain tasks. Rust is a systems programming language, so it must allow you to do low-level systems programming, which sometimes requires unsafe code. To write unsafe Rust, you simply use the unsafe keyword, and the unsafe keyword gives you 5 abilities that you don't have in the safe Rust world. The first ability is unsafe Rust. Unsafe Rust exists for two reasons. Reason number one is that static analysis is conservative by nature. So Rust will reject a valid program if it can't guarantee that that program is memory safe, even though you as the developer know that the program is memory safe. The second reason is that the underlying computer hardware is inherently unsafe. If Rust didn't allow you to do unsafe operations, then you couldn't do certain tasks. Rust is a systems programming language, so it must allow you to do low-level systems programming, which sometimes requires unsafe code. To write unsafe Rust, you simply use the unsafe keyword, and the unsafe keyword gives you 5 abilities that you don't have in the safe Rust world. The first ability is to dereference raw pointers. The second ability is to call an unsafe function or method. The third ability is to access or modify a mutable static variable. The fourth ability is to implement an unsafe trait. And the fifth ability is to access fields of unions. It's important to understand that unsafe doesn't turn off the borrow checker or disable Rust safety checks. If you have a reference inside of unsafe code, it will still be checked. So even though you have access to those 5 abilities I mentioned previously, you still get some degree of safety. Unsafe code isn't necessarily dangerous, but the onus is on the developer to make sure that memory inside of unsafe blocks is handled appropriately. People make mistakes, so writing unsafe code could introduce memory issues, but if you keep your unsafe code small and isolated, then those issues will be easier to debug. You can also enclose unsafe code in a safe abstraction and provide a safe API, which we'll talk about later in this video. All right, now that we have some background, let's go into each of the 5 abilities unsafe Rust gives us. In chapter 4 of the Rustling book, in the dangling references section, it mentioned that the compiler will ensure references are valid. Unsafe Rust has 2 types of raw pointers that are similar to references: a mutable raw pointer and an immutable raw pointer. Immutable raw pointers are written as asterisk const and then the type that the pointer points to. Mutable raw pointers are written as asterisk mute and then the type the pointer points to. Note that the asterisk here const and then raw pointers that are similar to references: a mutable raw pointer and an immutable raw pointer. Immutable raw pointers are written as asterisk const and then the type that the pointer points to. Mutable raw pointers are written as asterisk mute and then the type the pointer points to. Note that the asterisk here isn't a dereference operator, it's simply how we declare raw pointers. In the context of raw pointers, immutable means that the pointer can't be directly assigned after it has been dereferenced. Let's quickly go over some differences between references and smart pointers compared to raw pointers. Raw pointers are allowed to ignore Rust borrowing rules by having mutable and immutable pointers or multiple mutable pointers to the same location in memory. Raw pointers are also not guaranteed to point to valid memory. Raw pointers are allowed to be null. And finally, raw pointers don't implement any type of automatic cleanup. In the following example, we're creating an immutable raw pointer and a mutable raw pointer from references. Notice that we don't see the unsafe keyword anywhere. Rust allows us to create raw pointers, but it doesn't allow us to dereference the raw pointers unless it's in an unsafe block. Here we use the as keyword to cast an immutable reference and a mutable reference to their corresponding raw pointer types. Because we created these raw pointers from a reference, we know that the memory they're pointing to is valid, but in general, we can't make that assumption for raw pointer types. For example, let's create another raw pointer pointing to an arbitrary memory address. Here we're defining some random address, and then we're creating a raw pointer that points to that address. There might be valid memory at that address, or there might not be. We have no idea. Trying to use arbitrary memory is undefined behavior. The compiler might optimize this code such that there is no memory access, or we might get a segmentation fault. Usually there is no good reason to write code like this, but it is possible. Let's go ahead and delete this code, and then dereference R1 and R2. In order to dereference raw pointers, we have to use the unsafe keyword, and in this case, we're going to create an unsafe block. Here we use the dereference operator to dereference R1 and R2 and print out the value. So let's go ahead and run our program. And as you can see, R1 and R2 are both 5. Note here that we created an immutable raw pointer and a mutable raw pointer pointing to the same location in memory. If we were to create an immutable and a mutable reference to the same location in memory, then our program would not compile because that would be breaking Rust ownership rules. Raw pointers allow us to bypass the ownership rules, but we have to be careful because this might create a data race. Even with all the dangers, raw pointers are still useful, especially when interfacing with C code or building up safe abstractions that the borrow checker doesn't understand. Next, let's talk about the second ability we have in unsafe Rust code, which is the ability to call an unsafe function or method. Unsafe functions and methods look the same as regular functions and methods, except that they have the unsafe quickly. It means that when calling functions block, bodies of unsafe functions over unsafe code. Just because a function contains unsafe code doesn't make it an unsafe function. In fact, you can wrap unsafe code inside of a safe function. As an example, let's look at the split at compile time error saying this operation is unsafe and requires an unsafe function. Let's have a vector v, and then we create a mutable slice named r. Then we call r.split at mute, passing in 3. Split at mute will return a tuple containing 2 slices. Here we're destructing that tuple into the variables a and b, and then we're asserting that a is, rather than implementing a method that takes a in a variable named len, and then we assign inside the tuple an error here, and the error message is cannot borrow slice as mutable more than once at a time. When we're creating this tuple, we're mutably borrowing slice twice in the same scope. The borrow checker can't understand that we're borrowing different parts of the slice. All it knows is that we're borrowing the slice mutably twice within the same scope, which is not allowed. In this case, we know our code is okay, but Rust isn't smart enough to figure that out, which makes it a good time to use an unsafe block. So let's replace this implement, store the length of the slice inside a variable called point is parts mute. That's the pointer this about functions that call and use is which common. We also have to add this no mangle annotation to let the Rust compiler know not to mangle the name of our function. Mangle knows exact compiler change offset is valid. That's why in order to use these functions, we had to create an unsafe block. By looking at the code and asserting that this midpoint is valid, we know that the raw pointers used inside of this unsafe block are valid, and therefore this is an appropriate use of unsafe. Note that even though we have an unsafe block inside of this function, the function itself is safe and can be called from safe Rust code. What we've done is created a safe abstraction around unsafe code. Next, let's talk about functions that call external code. Sometimes your Rust code may need to interact with code in a different language. For this purpose, Rust has the extern keyword, which facilitates the creation and use of a foreign function interface, or FFI. A foreign language interface is a way for a programming language to define a function that another language or a foreign language could call. In this example, we've set up an integration with the ABS function from the C standard library. Calling a function defined within an external block is always unsafe because we don't know if the language we're calling into has the same rules and guarantees as Rust. It's the developer's responsibility to make sure that the functions defined within an external block are safe to call. Within an external block, we specify the name and signature of the foreign function we want to call. The C up here defines which application binary interface, or ABI, the external function uses. The ABI defines how to call the function at the assembly level. The C ABI is the most common ABI and follows the C programming language's ABI. We can also allow other languages to call our Rust functions by using the extern keyword in the function signature. We also have to add this no mangle annotation to let the Rust compiler know not to mangle the name of our function. Mangling is when the compiler changes the name of a function to give it more information for other parts of the compilation process. Here we want to prevent that behavior so that external code knows exactly what the name of our function is. Next, let's talk about the third ability unsafe Rust gives us, which is the ability to access and modify mutable static variables. Up until this point, we haven't talked about global variables in Rust, which are supported but could be problematic with Rust ownership rules. If two threads are accessing the same mutable global state, then it could cause a data race, for example. In Rust, global variables are variable a string and name data. Constances declare a function called add to count main with to implement an unsafe trait. A trait is unsafe when at least one of its methods is unsafe. We can mark a trait unsafe by adding the unsafe keyword to its definition and also to its instance. Unions are primarily used to interface with C unions, and it's unsafe to access fields of a union because Rust can't guarantee what the type of data stored in the union is for a given instance. If there's one thing to take away from this video, it's that using unsafe isn't wrong or frowned upon. When you have a use case for unsafe, then go ahead and use it. Just make sure you're being safe with memory. Alright, that's it for this video. If you enjoyed it, then no matter what, do not hit the like button. And if you want to see weekly Rust content, do not hit subscribe and definitely
So my name is John, for those of you who don't already know me from one medium or another. So one thing I keep observing about the Rust community is how we're all like allergic to unsafe code, or we think that unsafe code is totally fine and nothing to worry about. And I wanted to take a little bit of time to talk about what unsafe is, because I think a lot of where the community's lack of alignment on this particular topic comes from the fact that unsafe is a bit of a mystery to many of us, and I think I want to solve that problem. I'm not of the illusion that I can solve this problem in like 25 minutes, but I will try. So in this talk, I'm going to try to demystify unsafe. I'm not going to teach you how to write correct unsafe code, but I am going to try to explain some of the reasons why you might actually want unsafe, and some of the reasons why you should be careful about unsafe, and it is not something you should use just sort of willy-nilly. You could also sum up this talk basically as it's just C versus it's certain doom. Neither of these extremes are correct. And it's very important that we all agree on this. Like, writing unsafe is not just writing C code. It is more dangerous than that, and I'll explain how. But it's also not certain doom. There are a lot of things that unsafe is necessary for or useful for, and we need to acknowledge that as well. And so I want to go through first why we need unsafe. Like, why do we have unsafe in the language in the first place? Right? Rust is supposed to be a safe language. Why unsafe? And it turns out there are a bunch of reasons why you need unsafe. In particular, unsafe is there to ensure that we can write code whose safety relies on invariants that the compiler cannot check for us. And I'll go through some of these examples as we go through these slides. But the idea is that in unsafe code, we are the borrow checker, because the borrow checker cannot check whatever it is that we are doing. And not just borrow checker, but more about the sort of safety guarantees and requirements that Rust has. The first example of this is working with hardware devices. So when you work with hardware devices, and let's say you want to show something on the screen when your computer boots. At this time, like, there is no operating system. All you have are just like raw pointers that are specified in like the Intel manual or the BIOS manual or the manual of some obscure thing from the 80s. And so you happen to know by magic that at this address in memory, there's a chunk of bytes that you can write to and then text appears on screen. It's true. This is where you can write stuff to write things on screen during boot. The compiler has no way of knowing this. This is something you know as the programmer. And you know that no one else is writing to that address right now because you're in boot mode. Like, there is nothing else. There are no threads. And so you know a bunch of things that the compiler does not. So you can write this code, right? You can cast this pointer to a mutable pointer and then turn it into a mutable slice. You know that this code is safe. At this moment in time, the compiler has no way of knowing. Writing this code anywhere else, like in your regular like fn main, would not be safe. But it is safe during boot on hardware where you know this pointer is mapped. This is the kind of stuff we're dealing with where unsafe is necessary because the compiler has no hope of checking this code. Another example is when you want to interact with external code, right? Imagine you want to call into a C library, or maybe the C library is really like Java through J and I or something like that. The compiler has no idea what that code does. For all it knows, like, it's just going to write zeros to all of memory, right? It has no clue. You are asserting that you know that the code that this ultimately calls doesn't do something stupid. You're asserting that that code upholds all of Rust's safety guarantees. The compiler can't check it for you. It has no way to do that. And so you need to use unsafe to tell the compiler that you have checked. Another place where unsafe comes up a lot is when writing concurrency primitives, right? Imagine that you want to implement the mutex type. What does the mutex type do? Well, internally, it holds just a straight up pointer to some place in memory that sometimes it gives out a mutable reference to. The compiler has no way to know that we are carefully checking all of the invariants to ensure that we only ever give out a mutable reference to that pointer to one thread at a time, right? Like, this is the API for mutex, right? When you lock, it's going to do some kind of atomic. This is not how all mutexes are implemented, but this is one example where you're going to just like compare and swap a value until it becomes true. And at that point, you know that no one else is in this segment of code. No one else has a mutex guard. And so it is okay for you to implement deref mute for that guard and give out the mutable pointer. But the compiler can't know this. The compiler doesn't know that no one else is swapping this back to false, right? And so we need unsafe to tell the compiler that we have carefully read our code and we know that is the case. There is another category that I'm hesitant to even raise, but I think it's an important one when we talk about unsafe, and that is overcoming borrow checker limitations. There are some patterns that the Rust borrow checker is not quite smart enough to figure out yet. Usually these are already known issues, and you can look them up on like the Rust issue tracker. One example of this is if you want to return a reference early by downgrading a mutable reference. So this function right here, if you have this sequence of functions, this will not compile currently on the Rust compiler under the current borrow checker. It's a known bug, and it's something that you have no way of writing this code correctly that the borrow checker will accept. And so you can fix this with unsafe. You probably shouldn't. Like, find a different way to write your code. That is probably better. And this is also why I'm not showing you the code to work around the borrow checker here, because you probably shouldn't do it. Generally, if the borrow checker tells you that your code is not safe, it's right. And if you get into the habit of like forcing it to just like, yeah, I know what I'm doing, you're probably wrong some of the time. And that can have really bad consequences, as we'll see later. Usually, with the borrow checker, it's better to either write your code slightly differently or just wait a bit. The borrow checker is improving day by day. We also have Polonius, this new sort of borrow checker iteration that's coming down the line, which will fix many of these problems. The last category that comes up a lot is performance optimizations. And this is maybe the most contentious way to use unsafe, where there is a safe way to write your code, but you chose to write it in an unsafe way because you wanted like the very last ounce of performance out of your code. And sometimes that really is necessary. But I urge you to measure first, and preferably twice. It is very rarely worth that marginal performance increase that you usually get at the cost of what adding unsafe to your code introduces. Because now suddenly you are telling the compiler that you have checked some invariant that you need to make sure holds for all eternity going forward in your code. It is much easier to just not have that responsibility. If you do measure and you find that it's necessary, then do it. Unsafe is there for that, but be very careful. Now that I mentioned some of the reasons why you might need unsafe, I also want to talk about the ways in which unsafe can go wrong. Because this is like, your dereference is a real problem. Remember that with unsafe, we're telling the compiler that the code is okay. We are telling it that we check violates and escape. No compiler assumes learn what they are, code, whether safe or unsafe, always follows all of these rules and a couple of more. It assumes that no code ever dereferences a dangling or unaligned pointer. It assumes really no unsafe as to what a valid value even is in Rust. Is any bit pattern a valid F64? Valid. It's not clear. I think the Rust spec currently says it has to be 0 or 1. Trying to take any other bit pattern and casting it to a Boolean is undefined behavior. And you need to be aware of all of these rules if you are to write correct unsafe code. Some of them may not apply, and in some cases, the ways in which bad unsafe code relate to these might be hard to discern, but it's worthwhile to keep in mind that these rules always apply to you. So what are the effects? Like if you break one of these, what happens? Well, usually incorrect use of unsafe is undefined behavior. Not always. There are some cases where it's not, but usually that is the case. And undefined behavior is like playing Russian roulette. Okay? I cannot say this strongly enough. That when you use unsafe code incorrectly and you end up with undefined behavior, you have no guarantees what your program is going to do. And the effect ranges from none to your program segfaulting to arbitrary data corruption in memory. And think about what that means. That could mean like your code takes an entirely different path through your program. The wrong data gets stored in your database. The access check gets flipped from a false to a true. You have no idea. Worse than that, when you have undefined behavior, the effects may not appear today, but then suddenly appear tomorrow. Even for no reason. Like it might depend on your hardware or the hardware the person's running it on. It might depend on the exact compiler version. It might depend on the phase of the moon. You do not know. And that is why you need to be so careful with undefined behavior, because it's very hard to predict where it's going to go. You basically have no guarantees. And in all code you write, you should avoid undefined behavior. Like it is just never okay. So let's look at some examples of things that can go wrong. So there's some code on the slides here. I want you to look on the left side first. So on the left side, I have a function compute, and it takes an immutable reference to a number and a mutable reference to a number. And if that number is greater than 10, then it sets the second number to be 1. If the input number is greater than 5, then it doubles the second number. In Rust, the compiler is allowed to assume that the code on the right is the same as the code on the left. That is, it's allowed to assume that it can just read the left value once and just sort of cache it, and they can optimize away the double check for the if. And specifically, in C and C++, this optimization would not be legal because I and O, the two parameters to the function, could point to the same memory. In C, that is totally the case. And if they point to the same memory, then imagine what happens. We take this branch, but then we don't take this branch. That is possible in C, that is not possible in Rust. And so if you break the aliasing rules, as an example, right? Imagine that you have some value and you give out a mutable reference and an immutable reference to it. Someone could call a function like so you rely on. So you're going to take a function, relatively straightforward function, multiple times, push or to write into the next elements. This means that some of the elements in the vector
What do you love about Rust?
What I love about Rust, the ability to free the memory that you're using is directly tied to the stack. So whenever you create something, there's a stack variable or there's some amount of stack memory, whether it's a pointer off to the heap, a pointer and a length. So, some amount of memory on the stack and then some
Good
amount of
evening, friends of Rust. Welcome to our today's meetup, Rust. First of all, thanks, Stefan, for
Thanks you all for time during the talk when I say something that's unclear. I hope that's the idea, except of course there's a big asterisk here because there is this thing called unsafe code, and in unsafe code you can do all sorts of nastiness, like take a pointer to something, do some arithmetic to take it out of bounds, and then do an access, and now we do have an out of bounds access even though this is Rust. So most of the Rust code out there is completely written in safe code. This talk is not concerned with that. This talk is concerned with the, I don't have data, 1%? I don't know, the small fraction of Rust code that has to use unsafe for various reasons. Unsafe exists for good reasons. We needed to be able to write low-level, high-performance code that's correct for reasons which are too complicated for the compiler to understand, but it's a very sharp knife, and we have to be super careful in how we use it. So let's start a bit by seeing just how sharp this knife is. Once you start writing unsafe Rust, guaranteeing memory safety, guaranteeing all these nice properties is your responsibility. And this like a nice way to think about this is that you're kind of entering a contract with the compiler where both parties have obligations and kind of rights or privileges. And the key obligation of both sides is that on the one hand, the compiler is obligated to generate a binary. It might look like a nice magical wonderland and a good drug trip or something, but really it's more like a nightmare drug trip in all reality. I just didn't want to endure fear in the audience by taking the appropriate picture. So let's get Firefox to open things in the right window maybe. Let's look at one example of the weird things that can happen. So here's a little function, which obviously will always return true. Right? We're testing if some integer is either less than 120, equal to 120, or greater to 120. There's no way this function cannot return true. At the bottom of this here is a little thing with the main function which calls that function. And then if it returns false, states that the bad thing happened. And if you run this on current stable Rust, now I hope the demo gods are with me, then the impossible has in fact happened. This is the kind of stuff that can happen when you break your part of the obligation. Do not ignore the obligation. Of course, the annoying thing is that in many cases, like if you change this code just a bit, maybe like that, then the impossible will not happen anymore. So it's not like you can rely on strange stuff happening. It's just sometimes strange stuff might happen. And it might not happen on Mondays, but it might happen on Tuesdays. So this strange stuff happening, you failing to uphold your obligation as an unsafe code author, that is what we call undefined behavior in Rust. And you might have heard a related term, which I want to briefly talk about, even though most of this talk will be about undefined behavior. The related term is soundness. So soundness is a property of a function that you write. Like imagine you are a library creator author, you're using some unsafe code internally, but you're a good citizen and you want to expose safe to use functions to the outside world. Something like this call me function, which of course is completely silly to use unsafe for that. This is just for purpose of demonstration. So what does this function do? It takes a shared reference to a boolean. It does some pointer casting to turn this into a raw pointer to type U8, so we can kind of look at the underlying bits and bytes of the boolean. We do a load, we check if it's 2, which it shouldn't ever be because it's a boolean. And if it is 2, we call this hint unreachable unchecked, which is kind of the ultimate form of undefined behavior. If that code ever executes, we have immediate undefined behavior. And so reaching this line is an immediate violation of your obligation as part of this compiler programmer contract. And this function is sound, because no matter which kind of safe code you will write, a shared reference to a bool will always be true or false. It will always be 1 or 0. It will never be 2. So even though there is unsafe here, this unsafe is kind of safely hidden behind a typed API that uses the Rust types to express the constraints needed to make this thing safe to call. Right? If you replace bool by U8, this function would no longer be sound. Of course, if you change this a bit to maybe a raw pointer version of this code, like a star const here, then this might change. So what do you think? Is this still sound, or do we now have an unsound library? Yes, yes. Maybe I should. People raise hands. Who thinks this is still sound? 1/2 of a vote. Who thinks it's unsound? A lot more. So the main function. So those properties inputs you need to figure wrong about undefined behavior. And this is by far the most common one. People test their code. They run their test suite. I don't know. They write their whole program. They put it on the internet or something. And they say my code is fine. I tested it, so there can't be any undefined behavior. And we've already seen the example earlier, right, where I changed the comparison a bit so that always return true, still return true. It was still, that program still was wrong. It was just now it happened to be the case that the arbitrary thing the compiler did and is allowed to do when you violate your contract was actually the thing you meant it to do. That can happen. That's almost the worst thing that can happen because then you think you're safe, but you're not. Anytime you upgrade your compiler, you change people. The very compiler, my code broke, evil compiler. I mean, we try to avoid this, but when you have undefined behavior in the code, it's totally possible that it works with one compiler and then stops working later. That's just the nature of the beast. Some people think undefined behavior is something that compilers or compiler writers spend like days and weeks to find in your program, only to backstab you and break your code. That's not how it works. Compiler optimizations are just written under the assumption that there is no undefined behavior, and when assumptions get violated, weird nonsense happens. So it's not like compiler authors willingly doesn't. Even without optimizations, there's a whole bunch of stuff going on, even basic things here, but it's not what unsafe is not a thing. Even this was the 8. Unsafe code, know a lot more. If you thankfully just don't, I hope. But if you do anyway, and sometimes you place knowing the rules, but it can help you start behavior. Increase confidence in the memory result. You can just I use a few, and then if you're on the 92 chairs, one important point is framework, I think. Add, it would say, well, what do you have to ensure? But some of these requirements are a bit less local than that. We will see examples. So that